Okay, so I'll skip through this relatively quick because we already started late, but that's all right. This is a presentation on network streams. I'm Brian Hoover. I'm the test software architect. Oh, this is being shared, right? Everyone can see this?
Yes.
Yeah, we
Okay.
can see the screen.
Okay. Um, and I'm a LabVIEW architect. I'm a certified LabVIEW. I'm a LabVIEW champion, and I work at Samsung SDIA, where we make batteries for automotive qualified um, vehicles. So when we're talking about network streams, I wanted to first start and talk about inter-application communication. And so what we have really here is you might have a program and it has multiple independent running loops. And this is pretty common. You'll have a code module running the power supply, a code module running file logging, and a sequencer that might talk to all of them. And it's pretty common to need to communicate to these independent loops in various ways. And the most common ways are the ones that NI promotes, things like queues, user events, globals, functional global variables, channel wires. There's a whole bunch of different ways to have essentially data go to and from loops that are running. And this is pretty common. This is normal, basic LabVIEW stuff. Where we start to get a little bit more nuanced is when you have separate applications that are running. So imagine instead of one program doing all those tasks, we have multiple independently built programs. And you might want to do this for a variety of reasons, but one is it helps with the build process, being able to validate a piece of code on its own and then making changes doesn't affect that, it might not affect that thing. So if I make changes to the main UI, that doesn't need to revalidate the test sequencer if they're completely separate applications. But when you're doing this, you no longer can use queues and user events and global variables and those kinds of things because they're in different application instances. They're in different memory spaces that they don't share references. So we have to start thinking about other ways to communicate to them. And over the network is a pretty common one that can connect over local host instead of an IP address. And local host will just mean this computer that's currently running. Well, if we're talking over network communications and we have these separate applications running, we could also have them running on separate targets. So here's a very basic example of a couple of embedded targets running some LabVIEW code, and you have a Windows controller that or Windows machine that is talking to the controllers. And now we want to have these applications more or less distributed. Each of these controllers can do dedicated work, and maybe you have a central host that is telling all these clients to do work for them, taking measurements, maybe logging, doing actions. And the most convenient way is really to do it with some kind of network communication. And that's because these computers are networked together on some basic virtual LAN or wired network between them. So throughout this presentation, I want you to think of these three types of scenarios. The very basic one where you have one program, bunch of independent loops. You have multiple programs on the same machine, or then you have multiple programs distributed across multiple machines. And when we talk about network communication options, NI has this slide on their site that I've seen over the years, and it's supposed to be a very high level of what options are there. Shared variables, network streams, TCP and UDP, web services, and web sockets, which isn't necessarily shown here, but it's sort of like a web service in its performance and ease of use and configuration. And so NI just has a very high level, this is what we think you should use. These are the supported configurations. This is how hard it is to use it, that kind of thing. And it's no surprise that the ones that are the most easy to use are the ones that are native LabVIEW features. They're built in, they have tight integration, and NI can make it work really well. But those types of applications don't talk well with other applications maybe written in Python, C#. You have a web service, that'd be something that's easier to connect with for other external applications. So for this presentation, we're really talking about applications where LabVIEW is the client and the host. It's something that you can control. You're saying I can be the owner of the entire test platform. But if you had to interface with PLCs that are running certain things, you're more restricted. So that's why in this presentation I'm going to go with WebSocket, or sorry, network streams. I was reading WebSockets. Network streams because it's the built-in best LabVIEW one if you can stay in that tight NI ecosystem. Well, I guess you could argue TCP might be just as good, but then there's more work in setup. So that's why I'm discussing network streams. So a couple of network stream basics. It's a one-to-one connection only. So this doesn't mean you can't have multiple connections. It just means you'll probably have an array of connections when you're trying to have multiple targets or applications that you're talking between. So in this case, you can see there is one writer and one reader, and that's fine. But if you have like, for a web page, this wouldn't work well. You can't have 100 clients connect to it. You'd have 100 writers and 100 readers, and that doesn't really scale well. I realize you can throw it into an array, and that might be fine. But my point really is that this is a type of setup that's best geared towards few connections, having a few clients, not something like hundreds, because it's that one-to-one nature. But the data communication is lossless. It behaves like a queue with first in, first out. It's built on top of TCP technology, so it's relatively good performance-wise. And it's easy to change the data types. In this case, we can see they have doubles that are just wired in. Then when you write, you can write an array of doubles. And when you read an array of doubles. It's very useful to have these as a type def so that you can change them over time. Obviously, that will mean you need to build the new client and the new host if you change the data types. But it does help manage it well. And then on the surface, this looks really super easy. Like you can see these strings are the connection points. And so you just have a string called writer and a string called reader, and it just works. Yay. Well, it sort of works. It has problems with this type of very basic example. As soon as you start to say, I have a client that's an EXE, that's an application, but I have a host that's running in the development environment, then things break down, or maybe localhost doesn't work for some reason, or maybe my application name is shared between multiple programs. And so NI's examples, I'm not a big fan of them. And after I demo a couple, I'll probably highlight the things I don't really like. Speaking of demos, let's jump right into the first one. So this is a very simple demo. I don't want to spend too much time on it. I want to get to the later ones. But the things I just want to highlight about this is the demo that's shipped with LabVIEW. You can open it, run it. It works fine. But it doesn't work well as a full application. Things like a reconnect is something that I think is just kind of required for a real application. When I'm writing a real application, my network might go down. There might be a power outage and the switch is unpowered, or the cable gets loose, or for any variety of reasons, I might lose my connection to my client. And I need to be able to reestablish that connection. Something happened, a small blip, fine, let me deal with it, and I'll reconnect and get things going. This example doesn't have any of that. When one stops, the other stops. There's no, and then if one starts but never connects, there's actually no way to abort it because it'll wait forever for the connection that'll never happen. So there's a few things like that where it's like, okay, I get that you're showing off how to use network streams, but it's pretty limiting in the way that they show it. So if you open up the example finder, search network streams, here's this simple network stream project. And there's a host. Sorry, it's opening on my wrong monitor. And a target. So if we run the host, well, actually, sorry, I ran the target first, but it doesn't matter which runs first. And then here's the host. I can turn this knob and it changes it on the client side. And notice that my, I don't know how well this is being broadcast over video, but it's changing the sine wave and the square wave based on the frequency of the control that I'm putting in there. And if we stop one, the other one stops. The code
coming in clearly.
Okay, good. The code is, it's fine. You got two loops, one for the writer, one for the reader. So here's the host. It creates the writer. It creates the reader. Down here on a value change, we send that information. And then asynchronously, we're just continually reading. So there's no send a request and wait for a reply. It's just continually sending the request and it's continually waiting for replies. And for some applications that might be fine, but for some of the other ones, you do want that confirmation that the request made it there. So I prefer something where it is synchronous, or at least has the option to be synchronous. There are certain times that, of course, you don't want to wait and you just want to send stuff out. But if I'm taking like an analog reading, I'm going to ask my device to take the analog reading, and then I'm going to wait for that analog reading, unless it's something that's really long and I want to say trigger the analog reading, and then I'll come back and get it later. Logging is another example of where asynchronous is great. You just send some data, say log it. I got other things to do. I don't care how long it takes to log it. I'm going to move on. And that would be more applicable for this type of setup. And the target is similarly simple. You got a reader and a writer. The reader just sets the control value, and the writer just writes the sine and square waves that end up getting read back. But you'll notice here the data types, they changed, which is super handy because, as I mentioned before, they can be type defs. So up top, we're reading the double from the host side, and then we're writing this array of waveforms. And that's just changed from this little constant over here. Very neat. So when you're setting up those, what I wanted to mention as well, I know I mentioned it once, but I didn't highlight, is that that only works when there's not an application. When it's dealing with both are running in the development environment and both are sharing that string of connections. When you really want to go to remote devices or have separate applications, you need a little bit more, there's a little more nuance in the information that each the writer and the reader need. And so I have a couple of slides here dedicated to the kinds of things that the client needs to know and the kinds of things that the host needs to know. And this is just how I set it up. So if you're the client, what things do you need to know? Well, you need to know who I am, who the client's ID is, the name of me. I need to know an ID of the host, which is, similarly what it's going to be identified as. And these can be just any arbitrary names. They can be the computer names if you know that they're not going to overlap, or, target one, target two type of thing. You need to know the data type of the request and the response. And then you need to know the client application. And this is, again, so that you can have multiple applications go to the same client and be able to have multiple streams. For this, I'm just having a constant in there of client app, just to make things convenient. And then on the host side, what do you need to know? Well, you need to know what my ID is. What am I? I need to know the ID of the client I'm trying to connect to. I need to know the data types of the request and the response. I need to know the client application, just like before, it's a constant. And then this one, I also need to know the IP address of the client I'm trying to connect to. And you'll notice that the client doesn't care what the IP address of the host is. It can be connected to any host. It doesn't care. But the host needs to know where the client is, if that makes sense. And so with that, I have a much more refined demo that I'd like to show off. And again, all the source code to this is available after we're done. This is going to show multiple connections to clients. It'll show that this can be running in an EXE or source. It can be running on separate targets. You could have multiple clients connected at the same time. And it just opens up a lot more options for distributing an application among these different targets. And I will show that. And this is all in LabVIEW 2020, if it'll open. And then let me close some of these extra things. Okay, so here is the host, and I'm gonna run it. And by default, it just tries to connect to one. And I have this drop down to make things convenient for the demo that I'm gonna say, okay, try and connect to 2 local instances. And you got the little icon here saying that it's not connected. Well, I'm gonna spawn, how about 2 clients? So here's client 1. Well, actually, and then this is client 0. And now we can see that the host is connected. We have the little green icons. And I can change the knob, and we can see now I'm changing client 0. And let me select client 1, and I can change it, and now it's changing the other one. Now, these are running in the development environment, but they could just as well be running in applications. So I'll send a client stop request and another client stop request. And instead, I'll run this exe, which also asks how many clients do you want to run. And here's client 1, here's client 0, and we can see they're already connected. They have the green light on them. And that's because the source is constantly trying to make that reconnection. So client 0, here we are, client 1, works great. And I can, like if I stop one, it clearly stops it. But then if I start it back up, it will reestablish that connection, constantly trying to get that going. But this isn't just application on the same machine. Let's also demonstrate this running on remote targets as well. Because you can see on this project, I have a remote target that I can connect to. So here, this is a Linux RT virtual machine. So this is virtualizing an environment for the Linux RT, and it's basically pretending to be a C-RIO target. And if I say I'm connecting to 3 remote devices, and again, this is just for convenience sake, you can change the IP addresses here and the client names of what they are. So now, when I change the knob, I'm changing it over there. When I change this knob, it's changing it there. This all works. I have 3 separate clients now that are connecting to this remote device. This is as if it were a PXI or a CDAC or a C-RIO. And all I needed to know was the IP address of where it is and what I'm connecting to. So here, client 0, client 1, client 2. But both of these can also run at the same time. So let me go back to running that client. And it says, how many do you want to make? I'm going to make 2. And now my host has 5 connections, 2 of them on the remote target. I'm sorry, 2 of them on the local target, and 3 of them on the remote target. And any one of these just changes those. And they're constantly, they're having that retry connection. They have that status information. And I want this to kind of demonstrate, well, you could have multiple devices that were running locally. Maybe you were running all of this on one Windows machine, and you're realizing, oh, it's not stable, or it's too much performance issues. I can start distributing this among separate targets along the network, having them do part of the work, having them do part of the work. And maybe the Windows side is just reporting or being just an HMI, or maybe it is still doing some important stuff, but it's doing less important stuff. I can have it do, the logging side, the less critical tasks. Yeah, so that's what this is. And the source code to it, again, I'll share it and you can browse through it how you like, but it's on this command and response type of configuration. So when I'm sending a frequency, I have this one VI with the writer and the reader going in. And in it, I send the request to set the frequency. And then here I have a timeout waiting for the response. And that response will return to it that array of waveforms that is the sine in the square wave. Okay, any questions so far? I think I'm ahead of time so far.
Hey, Brian, have you tried to, I mean, this is great. This is the demo is awesome. So have you tried to mix network streams with TCP? I mean, in an ideal world, everything is LabVIEW, right? But I mean, now I have the need to interact with a lot of different applications, and TCP and UDP have come, to the table. And I was wondering if you have tried to mix these kind of applications using a combination of streams
Well,
and
I haven't done
TCP.
TCP and network streams simultaneously, but I have done UDP and
Mm,
network streams simultaneously. And I'm not exactly
okay.
sure how a TCP becomes a network stream. Like, I don't know what NI does to the TCP layer to add their special sauce, but it seems to be that it doesn't interfere with the basic TCP functions that are built into LabVIEW. So I would assume that they would work just fine, and that you could have your LabVIEW applications connect through network streams, and you could have your other clients connect through whatever. Now there is an argument saying, well, maybe they should just all use the same. And if that's the case, then maybe you should just use TCP across the board, or just web services, or just web sockets, or something like that. But at least from mixing and matching, I haven't had any problems.
Okay.
Yep.
Thank you.
So all the source code to the stuff I showed is available. However, in making this presentation and the demos, I kind of realized that there's some common functions, and we can make some reuse code that makes doing network streams a little easier for us. So I made a package, and I shared it on VIPM.io. And here's what the palette looks like, the client, the host, and the examples. And it's really just taking those common functions of how do I create a connection, how do I send a request, how do I get a response, how do I close it out. It's just wrapping those into some common functions that are easier to use. And because they're malleable VIMs, the data type can change throughout. You put in your type def just like you would with a normal network stream, and that type def will work its way all the way down to where the network stream is created and be able to come out as the request with that same data type. So if you're not familiar with it, you should go to VIPM.io. Let me show. This is what the page looks like. You can publish, any package for the community to have access to. They have a small review process, but there's information on it. There's posts about how to use it. Sometimes there's video or demos of it being used. And you just click install with VIPM, and it shows up on your palette just like any other VIPM package. So I'm going to start showing the demos from that package. And again, that'll be available for you guys to download and try out. But it's relatively straightforward, especially the first couple, because they're all on the palette and easy to use. So if you go to the block diagram and find the Whova palette, because this will show up after that package is installed, you have network streams, and here's the client stuff. So it's creating a network, sending the response, getting the status, converting the request so that we know what to do, and the host has a similar set of functions. Well, here are the examples. So I'm going to drop down the first one, and it's again a command response type of function. So I'm going to say add 1 and 3, and I hit click send, and there's my result, 4. Not very interesting, but the way that it does addition is what I think is the special sauce, the coolness. So this is both a client and host running in the same application. And this goes back to earlier where I said a better way of doing this would probably be with user events or queues or something else. But it demonstrates what's possible to then be sent out to separate applications or targets. So on the top, it's the host. We need to know the IP address of the thing we're connecting to. We need to know what the client's name is, what the host name is, and then the data type of the request and the response. And these are type defs, but this is that malleable VI that I was talking about. So the malleable VI by default is these variants, but as soon as you wire to it, it handles the rest of it. So in the front here, just like when you do like obtain queue, you have to tell it the data type. Well, I tell it that data type on this initialize, and it needs to match the client's data type down here. Otherwise, it'll generate errors. And then on the client side, we have this user event that's getting generated. So that is the user event of a request came in. So up top, when we run this VI, we're sending a request to do something that will trigger this user event to happen. And then we need to handle that and then send our response back. And there is a timeout. So like up here, I'm saying, wait forever because, well, this is using localhost. I really expect this to actually work. If this were a network communication, a real one, I might want to put in a 1 second timeout and say, well, if 1 second didn't connect and didn't get my request, then maybe error out or retry or stop the application, whatever you need to do. So that's this one, using user events, network stream functionality. Demo 2 takes it a step further and separates the client and the main. But again, these can be separate applications. So here's this. And I made these actually X nodes to bring up the folder. So when you click it, it opens a folder showing you where the client and the host are. So they're separate applications. Here's the client, here that's the host. Here's the client. So just like before, put in a couple of numbers, add, and I get the response. And then here's the client saying, oh yeah, this is the last request I got. Here's the last response I got. And of course, stopping it, you'll lose your connection. But if you run it again, oh, it didn't work. Oh, there we go. Whew, I was nervous. Took longer than expected. Then it makes that connection come back. It reestablishes it so that you know that 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 your application won't lock up if a network cable gets unplugged, kind of situation. And I did make these applications as well. I know I already demonstrated this for the other demo, but here is my client exe, and it's got a connection. And when I run it, it does the same thing. And of course, stopping the client now will actually close this program because it is a separate running program. And taking it another step further is just a demonstration I showed earlier, distributing this among separate applications, rather separate targets. And the only thing that has to be configured now is the IP address of where the thing is, because we know its name and we know its application name. Those were both constants that we put in there. We really just need to know the client and the IP address of the thing that we're trying to connect to. So close, close, close. Demo 3. Here's our folder. Host. And I'm going to, oh, I have that virtual machine still running. Too many windows. So here is the host, and here is the client that is starting up. Oh. Occasionally I see this, and I think it's a problem with the virtual machine itself. Oh, there we go. Okay. So in a real machine, maybe it wouldn't be so bad. But it's the same thing. I have this IP address. I have this remote target that is, you know, a PXI chassis on the network somewhere, and I'll have it do some work. And the connection is lost. And when I rerun the host, the connection gets reestablished. And the code for all of this is so very similar. We just say, where's the IP address of connecting to? What's the client's name I'm connecting to? What is my name? What is the type defs? And then in here, I have the value change event of here, sending the request, waiting for that response. I probably shouldn't have made that a -1. I probably should have made that some time with a timeout. And then here is this function for querying that connection status. These are actually asynchronous running VIs, so it shouldn't mess with your timing of your application. So you'll be able to say, am I connected? And it doesn't do an active connection now. It's constantly trying to connect, and it'll just return the status of the last connection or not. Okay, and now for my fourth demo, let me talk a little bit about 64 and 32-bit applications. So forget network streams for a second. Let's talk about application space. LabVIEW is one of those few programs that I prefer the 32-bit version of, and 64-bit programs have been around for so long. Like, that feels weird to me that when someone downloads LabVIEW, I have to recommend the 32-bit version. And that's just because not every toolkit is 64-bit compatible. But NI is pushing that more and more, especially with the way that Mac OS is going. They want to keep up with support there instead of having two separate versions. And so at some point, I'm I don't know this for sure, but at some point I'm guessing NI will push the 64-bit version and say, let's stop supporting the 32. Someday that has to happen. I don't know when. So I wanted to look into running 64-bit LabVIEW and seeing what limitations I have and seeing what problems I have to try and overcome to get ready for this migration that will eventually happen. And one of the first things I ran into is calling 32-bit DLLs in Windows. Microsoft set up 64-bit Windows to be able to call 32 or 64-bit binaries. They had to. There would be chaos if you just couldn't run your 32-bit programs. But they kind of siloed them to say that the 32-bit applications will have this memory space and the 64-bits will have this memory space, and they won't really come together. This does not have access to that, is basically what I'm saying. And so in a 64-bit LabVIEW program, you can't call a 32-bit built Windows binary. And that might be for like a DLL that talks to some hardware that you have. Let's say that the customer delivers some DLL for talking to a power supply. Okay, that works fine in 32-bit LabVIEW, but it won't in 64-bit. So what's your choices there? Well, if it's a third-party application, you're probably going to be left with having to either recompile or reinvent how it works, how it talks to that device. But there is an alternative that Network Streams kind of helps us get to. So here I have an example where a 64-bit LabVIEW can use a network stream to request that a 32-bit LabVIEW do some work. And in this case, it's calling a DLL that does an MD5 on a program, which really isn't all that amazing. There's dozens of ways to do MD5s and checksums that don't involve calling DLLs, or that there are 64-bit DLLs already in existence. But I wanted to do this demo because it was the first that I kind of thought of a way to demonstrate this working. So we can have that 32-bit LabVIEW call that 32-bit DLL. But because network streams work across even versions of LabVIEW, so I can have 2011 or well 2021 talk to probably 2015 or so without any real problems, I can also have it talk between the 64 and 32-bit versions of them, so that now I can have that 64-bit LabVIEW do work using a DLL that is locked down, or I don't have the source code to, or I can't recompile, or I can't reinvent how to talk to the device. And so for that, I have a fourth demo of my package. And I'm opening the 32-bit version of the project. So this is the 32-bit client side. And then this will get confusing with Windows, but I'm opening LabVIEW 64-bit. This just happened to also be LabVIEW 2010, I'm sorry, 2020, but it doesn't have to be. So now here is the 64-bit. Just make sure that it's opening correctly. And here is the host connection. And luckily, NI did make little icons that help to distinguish when one is 64 and one is 32. So here we have this, the color is a different shade of this orangey yellow. Okay, so here is the 64-bit program, and this is the 32-bit program. And so I can put in some file. Why don't I MD5 this random exe? And when I click get the MD5, what that does is over on the client side in the 32-bit, it gets that request. It said, here is the file. I want this file to be MD5'd. And you can see inside it, here is the request of the data type. And the response is going to be that MD5. Now, that works, but I could go more low level. that is a single function call to say, do my MD5. But using the second method, I can click it, and you'll see instead of sending the file path, it actually sends chunks of the file, one after another. And that's more akin to what the DLL call is actually doing. When you do a MD5 on a file, it's usually chunks of the file at a time. You'll read so much MD5, so much MD5, so much MD5. And what I wanted to show these two methods is because you don't have to call the DLL the same way. You don't have to create these interfaces. You can just use the functions that you most commonly use, or wrap multiple functions into a single network stream call. And honestly, that'll probably be more efficient rather than what's happening in this case. In this case, the 64-bit is reading the file and then sending a chunk and getting the response, and sending a chunk and getting the response, and sending a chunk, where I could send the entire path and say, well, just take care of all of it and tell me when it's done. And that's probably more efficient. This also works in applications. So I can have this program, the 32-bit, be built. I could have it running in the system tray. I could have it ran on startup, just waking up and ready and listening for a connection from the 64-bit version to say, do some operation or do some work. And then have that be handled by the 32-bit function, and then send the response over to the 64-bit. It's definitely it's definitely a strange use case for network streams, but in doing this 32 to 64-bit kind of translation, I discovered this and thought, well, this is a neat way to get around the limitations without having to have the source code, having it recompiled for a 64-bit, and without having any other translation stuff. And so if you want to open the source code, you can look at that. It's, you know, it's not as clean as the other stuff. I didn't quite polish it as well. But here is that 32-bit DLL that we're calling. Here we give the file path and we're saying perform the MD5. Or here's the separate functions of doing the initialize, updating the call with chunks of the file, and then finalizing it. But on the 64-bit side, it's really just calling that network stream request of do the various work that we want it to do. So here is the get one. We just send the file path. It gets the response. Or method two, this is a sub VI, that is do the initialize, do each chunk one at a time, and then do the finalize. And inside each of these is going to be a separate network stream of what it's going to be doing and getting the response back out. Okay, and so after all that, there's all those demos and all the source code and all the everything, and I wanted to show an actual real-life use case of it. Now this I can't distribute the source code to because this is an internal project and it's huge and there's tons of dependencies, but I can show you the actual application that network streams helped us out with. We had a program that is a Windows PC controlling this remote controller, and they're all running many different independent loops doing different things. So on the UI, on the Windows side, you have a UI, you have a sequence editor, you got report generation, you got file transfer, those kinds of things. And then on the real-time side, you have the actual test running. You know, you got CAN stuff, chamber stuff, cycler stuff, power supplies, DAC stuff, the sequence itself. And the communication between the Windows and the RT is primarily through network streams. So the Windows side will send a network stream request to the real-time side saying, do some work. And then the real-time side will send it back saying what it's doing or how it's doing. And this worked great, except it was kind of costly for what we were doing. The majority of the tests we were doing didn't require a real-time controller at all. It really just needed a Windows PC to do some manual control, to do some very basic stuff. And so without that much work, we were able to combine these two into one and have them use the same functions, the same code, and now what was network streams to outside applications can be either user events or network streams to the same application, to the same local host connection. And the same code is being used. The sequence editor, the CAN control, the power supply control, These are all things that have been unit tested and proven out and used very well. Well, now we can also just install this software on a laptop and do some very basic tests without needing the full real-time controller. The real-time controller is great for safety aspects, for reliability and determinism. But for some tests, we don't care about that. We just want to be able to do a test. Well, now the same code runs on the small laptop as the full test stand. The sequences that we write are portable. They can run on that full test stand or just any computer that we install this Windows software on. And that was because we wrote it with network streams in mind that then could be translated into network streams or user events that are local host related. Okay, so that's all for my presentation on network streams. And I usually just have a slide on the back saying various things I wanted to talk about. And so in this case, the GLA Summit, it's a free community hosted presentation similar to NI Week, November 15th and 16th. Go to this website, you can register. There's lots of cool topics that they're going to go over. And then LabVIEW 2021 is out. Here's kind of a list of some of the features: SFTP, show hidden controls, auto run is improvement, Python's improvement. There's various Mac OS improvements. There's the auto wire change, which has some mixed responses from people. But we didn't have a dedicated presentation to the LabVIEW 2021, so I kind of just wanted to throw a slide on the end and say, here, go check it out. Here's some features that if you're interested in, you can research.